Okay, so yesterday we have seen the optical property of snow and ice, spectral reflectance of snow and ice, and I asked you a couple of questions. I hope you would have really dwell on that uh, to make it easier for you to understand today's talk. So today we will talk about development of algorithm. Many of you who are working in the field of remote sensing are quite familiar with the idea of algorithm because algorithm is nothing but you prepare a finite list of instructions for a computer and then calculate a function. So in this particular context, our function is a snow cover. So if you really want to estimate the snow cover, it is necessary for us to estimate in comparison with other land features. And other land feature, if you really have a snow cover, is a vegetation, because many times there will be a lot of snow on vegetation or below the vegetation. Then there will be rock, soil, and water. And these are the fundamental land features which will be there. So we should be able to differentiate snow from these features. So we can do it if you have a unique spectral reflectance bands and information. Mm, uh, so what normally in satellite remote sensing, if you are using, then you should use a band or combination of band. Then you can estimate snow. So many of you are aware that if you have ever worked on the raw satellite data, then raw satellite data is nothing but the digital number. So we will go to that. But the question which you ask yourself is, can we use a digital number to do the further analysis? But we will explore that issue a little bit later on. But keep that in mind. And we have seen this curve yesterday. And in this curve, we have seen that snow has a very high reflectance in a visible band of electromagnetic spectrum. That means around 500, 400 nanometer to 700 or 800 nanometer. 700 nanometer, it has very high reflectance in this region. And when it comes to the sphere region, that means 1500 to 1700, 1550 to 1750 nanometers, snow has very low reflectance. So this is by any means very unique characteristic, a very unique reflectance. So key question is, can we exploit this typical characteristic of snow cover, where it has very high reflectance in one satellite band and very low reflectance in another satellite band. But it is also necessary for us to understand what is the reflectance curve in other land features. And so if you look into the other, like ice, if you look into the ice, then what happens is ice also has very high reflectance in a visible spectrum, and it has low reflectance in a near infrared spectrum or a sphere spectrum. And same story in contaminated snow. But when it comes to the rock or soil, then you can see that soil has a low reflectance in visible spectrum and very high reflectance in sphere. And if it comes to the vegetation, vegetation also has a low reflectance in visible and relatively higher reflectance in sphere band. So there is a possibility that we should have um, uh, a unique observation here, where snow reflectance characteristics are unique if you combine the visible and sphere part of electromagnetic spectrum. But if it is really a satellite images, and if it has very high reflectance, so this is IRS-P3 WIFS imagery, which is in visible and sphere region of spectrum, you notice the difference in tone of snow due to different reflectance characteristics. So you can see here that snow has very high reflectance and white in visible part of spectrum, and the same snow when it comes to the uh, near sphere region, it has very low reflectance, indicating that clearly indicating that this is reflected. The reflectance is reflected in a tone of satellite images. So this is very important observations you can make. So you can really do the simple scatter plot to understand what is the giving the reflectance of a major land features. If you plot it, then you can see here that you have a sphere band, which is the reflectance, and green band, which is another reflectance. So snow supposed to have high reflectance in green band and sphere and low reflectance. So it occupies this space. Another is a cloud, which is occupying another space. Then this is ice, which is occupying close. Then there is a rock, which is at different place, and the vegetation is also different place. So if you really look into this scatter plot, you can argue that snow and ice can have a unique space so that we can identify snow very comfortably on satellite images. So having said that, let us understand what we want to do. So you take a characteristics of the WIF sensor, which is in IRS P6 satellite, and you look into its characteristic of sensor. We have to realize one thing very clearly, that algorithm is developed for satellite sensor. So it is not developed arbitrarily for any other thing. So in order to do that, we have to have certain characteristic of that sensor. So in this particular case, we are looking into the AWIF sensor of IRS-P6. So you can see the first important thing is ground sampling distance. It generally means the spatial resolution of ground. So it is very, if you look into this, the sensors across the track and along the track. So along the track means it is in the direction of which satellite is moving, and across the track means the perpendicular by which satellite is moving. So it has a two, if you really look into the across the track, it has a 56-meter spatial resolution at Nadir. Nadir is the point which is exactly downstream from the satellite, and 70 meters off Nadir. Off Nadir means if you really look into swath of satellite, which is 740 meters, so extreme end of swath. So if you take Nadir at middle, so you have around 370 and 370 kilometers both the side, and 370 kilometers from Nadir, you will have 70 meters of spatial resolution. So you have a 56 meters at Nadir, you have a 70 meters of Nadir, which is at the extreme end of your swath. And then you have 66-meter integration time, and that means when satellite is moving in the direction, and if it collects the data within 9.9 milliseconds, then it will have 66 meter spatial resolution, because if it is not able to do within that milliseconds, then it is possible that you might have gap. So you have 66 meter, which is, so you have a three different spatial resolution. So, but many of you would have used the AVIF sensor, and you will always say it is a 56 meter spatial resolution. You never get this idea that it has a three spatial resolution. But eventually, when it is given to user, you integrate this or resample the entire data and give you spatial resolution of 56 meters. In a process, you are going to make certain compromises on your radiometry. You have to be very clear about this. So up to that extent, the original radiation characteristics will be slightly modified as we go on resampling. In addition to that, there is also swath, which I was talking about, is a 740 meter swath of satellite. So at a given time, satellite can make observation for 740 kilometers. Then it has a 4 spectral bands. It has 0.52 to 0.59, one spectral band, 0.62 to 0.68, another spectral band, 77 to 86, another spectral band, 1.55 to 1.7 is a third spectral band. But what really important is the quantization. So that is, it has a 10 bits quantization, and probably now it has, at that time, is a P6. At that time it was 10. It might have gone up now in a latest AVIF sensor. So quantization is very important because it provides you opportunity, but a small change in reflectance, how many pixels you will have to detect those. So quantization or dynamic range in that sense is very important for us. So the radius setting, that means it is also very important. So band 2 have a 53 microwatt per centimeter per steradian per micron. That means it is 100% albedo. That means if incoming solar radiation will be 53 and if 100% it is reflected, then it is, it is a maximum you expect that this much radiation will be received by satellite. And B3 is a 47, B4 is 31.5 and B5 is 7.5. So it also depends upon how much solar radiation is coming from the sun on the ground surface, and how much is solar radiation is emitted by the sun. Depending upon that, it is done. But don't be under impression that when you go to the next slide, you can see you can have actually incoming radiation which much more slightly higher than this also. It is possible in certain circumstances. So what it means? It means that in a band 2, if satellite sensor receives more than 53 milliwatts per centimeter square, then it will get saturated. So if it receives 54, 55, 56, 60, 61, it will show only as a 53. That is how this radius setting. Satellite sensors can have multiple radius setting, but those who are operating satellites never like this idea of using multiple satellite setting, because that is something has to be moved into the satellite from Earth, and it is quite possible that they can mess up with, because then it becomes a mechanical operation. It may succeed partially, it may succeed, it may not succeed, and because of that it can create the problem. So multiple settings are there, but there's extreme reluctance from those who are operating satellites to use those facility. But in this particular case, this is the one which is commonly used. Then you have band-to-band registration is plus minus 0.25. What it means is there will be shift. Once we have band 2, band 3, band 4, band 5, they should actually superimpose exactly each other. But you can have some error into that, and that is reflected into this. So having said that, we have looked into the spectral reflectance of ABIF sensor, band 2 and band 5, and we know that band 2 has a very high reflectance for snow and band 5 has very low reflectance. So you convert this into normalized difference. So, and that is called normalized difference snow index. Idea behind normalized difference snow index is you have a numbers which are manageable. That means if you take only ratio, numbers could be very large or you will find very difficult to put the threshold. But in this particular case, one moment you normalize, you can have a -1 to +1 number, and because of that, this is a commonly used. And if this particularly band 2 and if you can change combination, and this thing is also called something else. You can do it for vegetation, or you can do it for water. You can do normalized water index, or you can call it NDVI, normalized difference vegetation index. So this is called normalized difference snow index. So because it uses spectral characteristics of. So if you really look into this work is done by one of my doctoral students, who is now a very senior scientist in the DRDO. So you can see that how NDSI, if you take the spectral band, AVIS, that means we know the spectral band of AVIS is 0.5 to 0.9 and 1.55 to 1.7. If you take this spectral band and try to develop the NDSI, how it looks like. So first look at the reflectance of these objects. So reflectance of this object is, if you see the AVIF sensor, the spine has around. Okay, so now we were talking about the spectral reflectance of various land features, because this observation was done in Dhundi Observatory in Himachal Pradesh, in Manali, and the doctoral work of Dr. Negi, who is currently in Snow and Avalanche Study Establishment. So what you can see here is how is the spectral reflectance curve. If you can see here band 2, which is 520 to 509 nanometer, then you can see that how much is the reflectance is 0.49 is the reflectance in pine, deciduous, 0.82 is wet snow, very high wet snow 0.76, and water is 0.52. So you can see here how different land features have a different spectral reflectance. So you can remember, look here that wet snow and very wet snow, even though as snow changes from wet to high wet snow, there is a reduction in snow albedo. That also you can see. What it can say is, and if you look into the band 5, which is a sweet band where we're supposed to have low reflectance, you can see here wet snow has 0.041 and high wet snow has a lower 0.016. So as it changes, it is quite significant reduction in reflectance takes place. So if you look into the NDSI, if you use this reflectance curve, reflectance numbers, and you convert it into NDSI, you can see here is minus 0.46 is pine, minus 0.716 is deciduous forest, then wet snow is a 0.94, then very high wet snow is 0.95, water is 0.96, and cloud is 0.226. What it means is that you have a confusion between the water and snow. But other land features such as pine, deciduous, or cloud can be, or vegetation can be separated from this, but water and snow can still have a confusion. But it is also for us important to understand that So we have ability now to look into the unique, we have ability to look into the unique reflectance characteristics and convert it into normalized difference snow index, and we can map a snow easily. However, there could be a confusion or mixed pixel of water. What to do with that? We will look. That is the purpose of also algorithm. We will look into that very later stages. So before that, it is important for us to understand we should get the correct reflectance as well as correct NDSI values. If incoming solar radiation is contaminated by various other features, we should have ability to separate out so that we can get the correct terrain parameters from that or correct reflectance of the terrain. So we know that this is a sun and sun's radiation. Once it enters into the atmosphere, it gets attenuated, and when it gets attenuated, that means it is scattered and it reflects in all directions. So it is quite possible. This is a sensor where it receives the solar radiation, incoming solar radiation. It is quite possible that some of the scattered radiation from the atmosphere can go up and enter into our sensor. So you have this atmospheric scattering phenomena, and because of radiation reaching to that. So that is known as path radiance. So we should have ability to identify how much is the path radiance is coming so that we can get correct reflectance of surface. The once radiation is incident, it's fallen on the surface, it reflects, and it reflects into the atmosphere, and energy transmission, it passes through the transmission and reaches to the sensor. So you have, but how much is terrain element? That is important. It depends also on bidirectional reflectance function. It is a mathematical description of how reflectance varies for all combination of illumination and viewing angles of given layer. So what really happens is as season changes, sun's position is changing. Even though you may take satellite observation at one time at 10:30 or 10 o'clock or 11 o'clock, whatever may be your standard time, because that has to be set into the sun synchronous orbit. But with the season, sun's position is going to change. In addition to that, terrain is not also is a uniform. It is the undulating terrain. So sun angle, incident rate angle will change depending upon the position of terrain. That means it's a slope angle and orientation angle. We will look into this issue subsequently. So this is a mathematical of all these aspects. When you come together, you call the bidirectional reflectance function. We will not go much depth into that. But key question is, how do you estimate the radiance from the digital number? So what it means is, digital number is nothing but it depends upon quantization, or it depends upon the how much is if you look into the sensor characteristics, it is only function of quantization. How many bits is the data? So if it is a 2-bit, 3-bit, 4-bit, 5-bit, 10-bit, so depending upon that, whatever the incoming solar radiation it receives, if it receives from 50, so it is split into 10 raised to power minus 2 raised to power 10. That is a quantization. That is how it is split into that. So this is just a number. It doesn't reflect. It doesn't tell you about the how much is energy is reflected from the surface and how much radiance. So that is called radiance. Radiance is the energy which is reflected from the surface. So the digital number needs to be converted into radiances. So digital number is there's some procedure for calibration procedure for that, and you have before you send the satellite into the orbit, you have a calibration of sensor. That means if you have a minimum, minimum should be 0, but it is you take at the minimum, and the maximum, how much is a spectral radius, and then you have a digital number. So if you have 250 digital number, you convert this into, you create this slope, and this slope is used to convert digital number into radiances. What it means is, so slope, G slope is the response function, and B is the intercept of response function. So B is here, that means it should be at 0, but instead of that, it is, you have some value added into it. So you have L minimum is a spectral radiance. So, so if you want to have L lambda, which is nothing but the radiance, then you have L maximum, L maximum, L minimum, and L maximum. L maximum is the spectral radiance of Dn. Maximum, how much is the minimum, which is generally 0. The bias or calibration set off, this is a bias or calibration set off, and then L, you add this value L minimum here, and you get the radius number. You will do some of those exercises in a due course during this course also. So mean solar, what essentially you do is, you try to do it initially that above the atmosphere, because you receive the energy above the atmosphere, because satellite is above the atmosphere, and then what you do is the incoming solar radiation, you know how much is above atmosphere, how much you received above the atmosphere, and try and get it be reflectance, which is exo-atmospheric reflectance above the atmosphere. So mean solar exo-atmospheric spectral irradiance. So now we are talking about another sensor, which is IRS-1C and 1D satellite, and it has at least 3 WIFs, and this is IRS-1C and 1D, and it has a different spectral band 2, 3, 4, 5, and it has, if you really look into these sensors, what I wanted to show you is, you understand how much is incoming solar radiation is there. And you can see here is incoming solar radiation in list 3 in band 2 is 185 milliwatt per centimeter per steradian per micron, but its saturation is 14. That means if maximum radius it can measure is maximum radius, and it is percentage. So maximum radius is a 14, and it percentage wise it is a 36%. So if total incoming solar radiation, which is X, then 36% of that at which the sensor will get saturated. What it means is that if satellite receives in band 2 any radiance or any energy which is more than 14 microwatt, it will get saturated, and it will show only 14. So it means 14, above 14, 15, 16, 17, 18, 19, 20 will show as a 14. Same thing you can see other. Key question is why it is done in this fashion, because some of the land objects for which this sensor was launched has very low reflectance, and because of that they have low reflectance, so they reflect very small amount of energy to make sure that you get a large number of dynamic range in this small amount of energy. You do this thing, so that is how it is done. But you cannot do a remote sensing application, particularly for snow, by using this sensor, because every time it gets saturated. So the radius setting you can see in AVIF is a 53, whereas it is in list 3 was 14. So it was really very low, and we have really difficulty in doing that. So if you look into the dynamic range, how it works out, as list 3 has 7-bit data, and it has 128 pixels you can have. and AWIFS has a 10-bit data and it has 1024 pixels. So what it means is, originally, when early days in 90s and early days, there was limitation of technology and they were not able to download the data in a speed. Because of that, the data is reduced, and that is how work was done. But somehow the work on glaciers, if you look into some of our earlier papers, we were not really working much on albedos and other kind of work, essentially because it was, at that time, satellite data was not really allowing us to do that kind of work. So what really happens is on above the surface, but what happens on the land? That is very important thing. So this is the estimation of reflectance from radiance. So once you have radiance, you need to convert it into reflectance. So in order to do that, reflectance of pixel in a particular band, you have this formula by which D is the Earth, Sun-Earth distance, E Sun is the mean solar exoatmospheric spectral reflectance. We have seen that. We have seen some of the this exoatmospheric reflectance we have seen here. This much is reduced coming from the sun. We know that. And cos theta s is a zenith angle. So what it means is, it gives the two crucial parameters. One parameter is giving how Sun-Earth distance, as it is an astronomical unit. As we move from mean, as Earth is tilted, it might vary minor here and there. So that is also influencing your result. And mean solar reflectance is not changing much, and this is giving solar zenith angle. And this is the cause of that, because it reduces with the cosine. So you use the cosine of theta s, and this means, what it means? It means if surface is not perpendicular to radiation, the radiation per unit area is reduced by cosine of solar zenith angle. Remember, I will try to explain to this, but remember this: if surface is not perpendicular, if surface is inclined, and then its incoming solar radiation is reduced by cosine of zenith angle. So let us understand what it means. It means that so you have a horizontal plane over here where it is horizontal, and you have sun, and sun is making certain angle with vertical, which is a theta s. So incoming solar radiation E into cos theta s. So this theta s is reducing incoming solar radiation. If it had been vertical, there is a different story, but this is theta s, it is using E cos theta s. But if surface is not, this is a horizontal surface, if surface is inclined, and if it is making angle of theta O, this is angle of theta O, and this is a vertical, and then this is a theta s, which is the angle which is made from vertical, and this is a perpendicular for that. So actually the angle between the perpendicular is a theta I. So theta s becomes theta O plus theta I. So incoming solar radiation is E cos theta I. That is how it will change, and because of that, it depending upon angle and depending upon orientation, it is quite possible that incoming solar radiation will change, and that incoming solar radiation is significantly going to affect its reflectors. It is not the reflectance of snow has changed, but your observation has apparently changed the reflectance. You understand? So you take, this is a curve. This is work which is also done for one of the doctoral thesis, and you can see this is a reflectance and this is a direction in which it is. Suppose you have 10 degrees slope, and then you have a reflectance. If it is northern facing, it is 0.4, and if it is southern facing, it is 0.8. So it appears to be, it has very high reflectance. So this is how reflectance is going to change very significantly depending upon its orientation as changes in slope. Even in northern slope, 10 degree, 20 degree, 30 degree, 40 degree, depending upon slope in an angle can also significantly change. Depending upon the direction, it can change. So it has a both way effect. If we look into all things, this is a both has a effect. Some places it is reducing, some places it is increasing around the slope angle. So this is very, that means if you really want to work on reflectance, you have to work on this very different, this idea that is you need to correct satellite reflectance for local illumination angle. So this is known as theta I is known as local illumination angle. So you need to correct it for local illumination angle. And top of that, we have seen the two aspects. One aspect is path radiance. You need to correct it path radiance, and you need to correct it for local illumination angle. So you have a complex work to do if you really want to work, get the true reflectance of snow. So key question is, can we really get rid of all this complex issue and try to simplify it? This is one of our paper published way back 2010. You can see here is now, this is a slope, which is a where it is sloping in north direction, and ABIP sensor has 0.5 and it has 0.017 reflectors in band 5. If you see it is west, then sloping or south sloping, you can say 0.85 and 0.1. Even though there is a large variation in reflectance, there is no difference in NDSI. This is a unique characteristic of NDSI, and why this is happening, I will leave to you. You do simple mathematical calculation and you can do it. So this is a great step forward in simplifying our procedure and our work, so that we can quickly get the snow cover without doing too much calculation on local illumination angle or path radiance, irrespective of you can do. So you can see that there are a lot of variation in reflectance in band 2 and 5, but NDSI values are really within 0.5, 9.7, and that variation possibly because of the way experiment was set up. I have not shown you experimental setup, but it was very unique experimental setup. We have done thanks to the people working in snow and avalanche study establishment at that time, which has created a special platform for us so that you can move the platform to ensure that we get the reflectance. We can put a lot of snow on that platform and keep on rotating the platform so that this orientation and direction keep on changing. So it was really very creative time in those days, and we did it, and you can see now this can be done. So another question is, we need to validate it. Really, that field validation of NDSI for different land features. So you have band 2 and band 5, which we are supposed to use for NDSI. So we have done it for fresh moist snow, refrozen fresh snow, high wet snow, then clean snow under shadow, and moist. So this aspect, I would like to dwell a little bit about the shadow concept. So what really happens is when you do satellite interpretation, particularly in a region such as Himalaya, and if you are taken satellite images around 10 o'clock, then you have a mountain shadow. So since it is in mountain shadows, if you use the ordinary technique by which you do the classification, the reflectance or radiances are very different and making it very difficult to identify snow under mountain shadow. But if you really look into that, it is NDSI is also very high here in mountain shadow. So one of the key application of this, not only it simplifies the procedure, but also it has ability to monitor snow under mountain shadow. And why is that? That is essentially because mountain shadow does not mean it doesn't receive any radiation. It doesn't receive direct radiation, but it always receives the diffuse radiation. And because of that, you have some radiation there. You can see the radiance is very low. So wet southern facing has 36 milliwatt. It has only 0.83, but still it is not zero. And that is helping us to get the reflectance. So it is a unique feature. If you see now that you can get rid of local illumination angle, you can get rid of path radiance, and you can get rid of shadows. So it looks to be very promising technique by which we can develop it. So normally all remote sensing people will do is first plot the scatter plot to show how NDSI and reflectance band 2 you can see. So you can see very clearly here vegetation is marked here, rock is here, fog is here, cloud is here, shadow, snow is here, snow under shadow is there, and water is there. So if I put arbitrarily 0.4 as a value, a threshold, where if snow is above 0.4 or NDSI is above 0.4, I will call it as a snow, and if NDSI is less than 0.4, I will call it as a non-snow. So I will give non-snow 0 and I will give snow 1. But having do that, there are two questions are important. Why to select 0.4? Why not 0.5? Why not 0.3? And another question is what you do with the water. Because water, still you identify water as the snow in this algorithm. So this is very important for us to understand, and we will try and dwell on this issue in the next couple of minutes. So another key issue is also your pixel may not be a pure pixel. What it means is if you take the satellite, so pixel might have partly snow, it might have partly vegetation, it might have partly a rock. So what you do with that, the mixed pixel. So this is another experiment was carried out, and there are a lot of publication on this. You can see that if a pixel is without vegetation, you have no problem. In the mixed vegetation, the 1/4 pixel is of vegetation, 1/2 pixel of vegetation, then NDSI values coming down. Still you can under 3/4 part of vegetation, you can still identify snow, that pixel as a snow, or vegetation. If it is full, then you cannot. So in that sense, NDSI is a robust algorithm or method by which we can really identify snow very clearly, even if it is a mixed pixel in that sense. So I want to understand what is the thresh value of this. So you do the sensitivity analysis to understand whether it should be 0.4, 0.5, 0.6, 0.7, 0.8. I don't know what it is. So what you do? What you do is you take a region which is predominantly covered by snow, and of course it will have small amount of vegetation, land, and other features, but it is predominantly snow, and try and do change its threshold value. So you start with 0.1, then say how much is area. You change it to 0.2, you see how much change in area, percentage change in area, you calculate, you go to 0.3, you go to 0.4, you go to 0.5, like that you go, and then you see where is that threshold is, from where this slope, from where we start losing the land. It means that is the point from where we start losing the snow. So that should be thresh value. So this is very close to 0.4. From here, the curve is started to lose certain land, certain pixels, and we call So that is how you can do it. It can vary from season to season. You must take it from me, and you can go. So as a conservative estimate, people have taken zero point 0.4, but you can do this experiment in your own way and try and analyze and do it. What is the zero point 0.4? Is it correct? 0.45 is correct. Many people have used fine tune this for debris cover or numerous other things. You can do it in that fashion. So when you do that, you can do that. So this is ABIF sensor. So let us look into this, how it looks like. We have said we have two uh, ideas. One idea is we have, this is where mountain shadows are. You can see there's a spot is there, mountain shadow. We can clearly identify on this snow in mountain shadow. So that is not a problem. Mountain shadow is not a serious problem. Then another issue comes as a, this is where clouds are there. So what do you do with the clouds? This is really a $1 million question, and there are no easy answers. If you are using only NDSI, is the character, is the feature. If you use thermal or any other data, then it is slightly different ballgame. If you NDSI, it has two problems. One problem is you can identify, if you have thermal band and other band, you can identify cloud clearly. But our idea, our algorithm is not about the mapping cloud. We want to know what is below the cloud. Is it snow, whether it is vegetation, or whether it is a rock? And that is where the difficulty comes, is there are some algorithm by which you can clearly mark the cloud, but what is the below the cloud is can lead to the a lot of confusion and difficulty in doing that. So we have then we have to algorithm has to be standardized, because algorithm cannot be just left as it is, and you cannot do the experiment every given day on that on each, because you received every 5 day satellite images 700 kilometers, you have entire mountain range, so practically you are getting 3 images per day. You need to analyze it and get the result. Whatever errors are there, that these errors should be known for what reason they are coming, and they cannot vary from pixel to pixel or imagery to imagery. So having said that, this is how that finally algorithm is fixed. You can ask certain philosophical questions on this, but let me explain to you how this was fixed at that time. And I am still under impression, if you get this was done way back in 2005, 6 or something like that, 7. And if you go back, still probably they are producing snow map by using this algorithm, but you need to check with ISRO. So this is ABIF data. You take band 2 and band 5. From there, you convert the reflectance image. From reflectance image, you get the normalized different snow index image. And if it is greater than 0.4, then it goes as a snow and water, correct? Then if it is less than 0.4, then it is goes as greater than 0.4, then it goes as a cloud pixel, and between 0.4 and 0, and if it is less than 0, then it is other pixels. So you remove the cloud pixel and you do nothing with that. Just remove the cloud pixel. Correct. And then you take other pixel which is less than 0. Then what you do, or this, no, sorry, these cloud pixels will go into this N5. So you take that. So you do one thing, you take the previous imagery, which is 5 days before you have acquired now. And here also you develop NDSI image, and you use this thing. And with the idea in this is, that whatever pixel is identified as a non-snow pixel will go through it again, the on satellite images, which is 5 days earlier than today. So if it is a 10th, if today is, if it is a 10th March imagery we are analyzing, then we go and a certain pixel identify 10 as a snow, they will go at snow. Certain pixel identified as non-snow, they go to the 5th March imagery again and identified as a snow and non-snow pixels, and with the idea that within the 5 days the cloud will be shifted, and then we have this imagery. So difficulty is now in ABIPS data is a water pixel. So what you do uh, with a water pixel is very difficult thing, because mm, it is a much more tricky question to answer, because it is question has to be answered on philosophical level. What it means is, you have a water body. It is much easier for us to take a water body in a summertime and remove that water body from the mass by using mass. It is one easiest way to do it. Second difficulty is that water in winter time will freeze, and there will be then snow on the ice. So whether you want to estimate that as a snow or you don't want to estimate as the snow. So a difficulty is there, and whatever may be your decision, some people you are going to make happy, some people you are going to make unhappy. So if you are a hydrologist, you would like remove those things, because that is not going to produce water into the river system. And if you are a pure scientist, you will say, okay, we are not monitoring whether snow is on land or snow is on ice. We are monitoring snow. If you take the glaciers, you monitor snow on glaciers also. So why not on ice body? So you take a call. Everybody has to take a call on that, whatever they want to do. There is no silver bullet answer for this question. So this is how you do, and then you have a 10 daily basin wise maximum snow cover. Why is that? Why is that? Because once you identify any pixel as a snow pixel, you are not going to examine that pixel again. This is the lacuna of this algorithm, that you are not visiting that pixel again. It means this pixel will be identified as a snow pixel. So in a 10 days time, if some pixel have got converted into from snow to non-snow, it will not be depicted here. Therefore, it is maximum snow cover. So this work, you can remove the cloud, and this is how NDSI image on product, you can see it was done. And this work was done from 2005 to 2009 till I was leading this program, that monitoring of seasonal snow with large number of basins. And I'm sure many of you, some of you might have also worked, might be working still in this program. This is still ongoing program to monitor seasonal snow in ISRO. There is also validation program where you can, it is much easier, you match the pixels. This is a classical way of validating the algorithm. That also you can do. You can also validate in a very different way. Mm, what this way is, this is opportunistic validation. What it means is, you take a geographical land, and historically you identify this region is is 100% snow cover. There is no other landform there. You take the satellite images, which is of non-snow season, summer season, and classify this into different categories. You categorize either snow and ice, barren land, sparse vegetation, dense vegetation. You identify this, create a mask, and just wait, 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 till you get major snowstorm in that region, right? And you have, and moment you have a major snowstorm, this satellite has a 5-day repeativity. So if you are lucky, you will get the next day satellite images. You have satellite images, then you do the classification and then say how many pixels they are actually supposed to be there, but how many are identified as a snow. So that is how you get the accuracy. So this is how snow and ice accuracy 99.6%, barren land 98%, sparse vegetation 98%, dense vegetation 65%. So that is how it looks like. There is a slight change in depending upon vegetation and other things. So you can see that this is also that. Another thing is the cloud, that how cloud cover can really influence the your result. You can see this is how the cloud, this all variation in accumulation melting. This is, you may tend to interpret, but this is only because of the difficulty cloud cover. But if you remove that, then you can get much smoother curve. And you can also do, when you remove all cloud and then the snow accumulation ablation pattern, you can get, one is for Ravi Basin, which is low altitude basin, and you can see even the middle of winter snow is melting. And if you see the Bhaga Basin, which is very high altitude basin, and it is melting in the beginning of winter, but it is really stable snow cover in the middle of winter. So this kind of use, you can use it later on for hydrological purpose and other things. So before I close this presentation, I would like you to go through some of these questions and try to answer yourself. I will not answer this question. So can we estimate NDA size in digital number? If yes, why? If no, why? Just dwell on it based upon our today's presentation. Why reflector changes in different slope and orientation? Why NDSI do not change on different slopes and orientation? That is also, I have not answered this question, but I'm sure by with this presentation you should be able to answer. Why we should use normalized difference than ordinary ratios? Try and do something on your own to answer this question. Why cloud gives the error in snow cover estimation? Can we use the temperature threshold to improve accuracy? Can we estimate the snow under mountain shadows? And can we estimate snow under vegetation? These are the questions I think you should dwell upon this. And thanks a lot. This was when I was much younger, and this was way back in 2004, photograph at Patsy Glacier. So